Hi everyone, this lecture is the discussion on the 4 examples of finite state machine, including the vending machine, finite string pattern recognizer, traffic light controller, and digital combination lock. For finite string pattern recognizer, I will also include how to make a simple test bench to verify the finite state machine in Verilog. For digital combination lock, you will see also in some system like this, a complete digital system normally consists of data path and finite state machine as controller. So when you identify the data path components, it will help a lot in FSM design because it especially in identifying what inputs and outputs that will connect to the FSM. So we will use the basic 6 steps here to design FSM. So the first step is very important, which is to obtain the specification of the circuit you want to design and make sure you understand as much as possible the specification. So some of the suggested techniques or steps you can use in understanding the spec will be discussed. Second, after you have a good understanding on what you want to design, then you can go proceed to create a state diagram and followed by a symbolic state table. And if in some cases you notice that there are so many states and some states could be redundant or equivalent to each other, you can perform the state minimization to minimize the number of states. The less number of states you need for your FSM, that means the less number of flip-flops required in this circuit, which will make the circuit smaller and more optimized. After that, we decide on the state encoding, for example, simple binary encoding or one-hot encoding when we want to perform the state assignment or giving the binary code, giving the coding, assign coding to each state. So this is necessary because at the end of the day, even you are using Verilog or you use schematic, we need each state to be coded. Okay? We need to give some binary values to each state. Okay? So then we come to the step of implementation. So there are 2 options. So you can implement using the schematic or gate level circuits. So or you can use Verilog coding to implement. So when you choose schematic, that means the following steps is to derive the next state logic expressions and also the output logic using the K-Carnot maps methods. So you derive the Boolean expression for the next state logic and the output logic, and then you can draw the gates that are connected based on the Boolean expression. If you use Verilog coding, then you don't need Carnot, then you just code it based on one of the simple methodology where you just code 3 always block. The first always block represent the flip-flops or state registers. The second always block implement the next state logic, and the last always block implement the output logic. Let's look at the first example, which is vending machine. So the first step is to understand the specification. So one of the way to understand the specification is you draw the block diagram of the system you want to design. So this vending machine is selling a gum which costs 15 cents each. So the vending machine has a single coin slot. That means at one time you can only insert one coin, and it only accept dimes and nickels, which is a 10 cents and 5 cents. So only 2 types of coins are accepted by this machine, and there's no change returned. That means the balance is not returned. If you pay 20 cents, then that's all. You need there's no 5 cent return from the machine. Okay, so this is a specification of the machine given, and one of the way to understand the problem is draw the block diagram. So draw the block diagram of the vending machine, and then based on the spec, you know that there is 2 inputs coming from the coin sensor to detect the types of coins received or inserted to the machine, and then there's one output only to indicate whether the gum will be released based on the amount paid. So drawing will help you to understand, especially you also try to draw other components outside the machine that are involved, like coin sensor, because from there you can see that coin sensor will produce 2 types of signal that will become the input to my vending machine. Okay? And then there's a mechanical part that will decide to release the gum or not, so that will receive a signal or instruction from my vending machine to release the gum. Okay, so with the drawing, it will help a lot for you to identify or further understand the vending machine, especially identifying the inputs and outputs needed in your design. And of course, all the FSM have a clock signal because FSM is a synchronous sequential circuit, and it's good to have the reset so that you can reset the machine to the initial state or the first state whenever reset is asserted. So step 2 is derive the state diagram. So you have identified the inputs outputs. So next you need to think what are the modes that your machine have. Even at the first time you're not sure, then you can start with state by state. So the first state you can start with S0 and then put an arrow coming in from outside that and then label it as reset. That means whenever the system is reset, it will come back, it will come to the state S0 initial state. And it is a good practice for every time you draw the state, then you put the meaning of the state as a note or remark. It will help you to expand the following states in a more correct and optimized way. Okay, so S0 is the initial state. That means the machine is still in the standby mode, waiting for the customer coming to buy the drink. So this since the only output which is open, since it depends on the amount of money received to decide whether open is 1 or 0, then the mode you define for the state should be related to the amount of money. So S0 is when there's no money received, so then we will proceed drawing the next state. So how many branches coming out from the state, the initial state, depend on the number of inputs. So you have two inputs, which are nickel 5 cent and dime 10 cent. So because the coin slot can only receive one coin at one time, so the outgoing branch from the state should be when n equal to 1, when 5 cent is received, when 10 cent is received, or when there's no coin received. So there's three situations you need to consider: when 5 cent coin is received, when 10 cent coin is received, or when it's still waiting, no coin received. So you cannot consider the situation when n equal to 1 and d equal to 1 at the same time, because that means two coins are inserted and sent at the same time, which is not possible to happen, because the coin slot designed for the machine can only slot in one coin at one time. Okay, so you just need to consider three situations for each state. So if n is received, that means if 5 cent is received, then the machine should enter a new state. Let's name it S1. So because S1 is just a symbol, so better you put the note. What is the meaning of S1? S1 means the mode when 5 cent accumulated in the machine. Okay, and then in another case, when from initial state, when only 10 cent is received, then it should enter S2. S2 means the 10 cent has been accumulated. Okay, so you use the similar way to draw. Okay, and then every time you draw, name use a symbol to name the state. Put the meaning, okay, then proceed until you reach at the end. How do you know it's end? It's end when the amount of money received is sufficient to release account. So for example, 10, this is 5 cent received, and then another 5 cent received. So S3 means 10 cent is accumulated, okay, as defined here. And then if the third 5 cent received, then S7 means 15 cent accumulated, then it should release the account. So this is a more FSM machine, so the output is labeled under the state. So you can label open under the state, that means open equal to 1 here. If those which has no label, like open label, that means open equal to 0 by default. Okay, so this is how you label. And then why is it good to put the remark or the definition of each state? Because from here you see, in case you have redundant states, you know it happened and you can merge them. For example, S2 and S3 mean the same thing. That means they should belong to the same mode. Then this S2 and S3 can be merged in the optimized state diagram. Okay. Same goes to S4, S5, and S7, which mean the same thing. And then S6 and S8 is the cases where the situations where 20 cents are received, which has extra 5 cents. However, because the machine cannot return any change or balance, so 15 cents received and 20 cents received mean the same thing. The situation, okay, the situation which is the situation where the sufficient amount of money has received and income can be released. So state S4 until S8 can be made equivalent and merge into the same state. So in the more optimized state diagram, you should have 4 states only. So just now S0, we can change the name. It's always good to have a more meaningful name for the state. So you can change the name to 0 cent, okay, which means this state means 0 cents is accumulated in the machine. Okay, you have 0 cent, and then when D bar and bar, that means when there is no coin received, then it will waiting in the same state. Okay, D bar N, that means when there is one coin received, which is nickel, the 5 cent, then it will move to the next state. Okay, when 10 cent is received, it will move to the 10 cent state. Okay, same goes to the 5 cent. There's a situation when no coin is inserted. Okay, after the customer insert the first 5 cent and then waiting to take up the next coin, then that is the situation when no coin is inserted. So the machine will look in the same state waiting. Okay, and then after that, after some time, let's say a 5 cent is inserted, then because previously already got 5 cent, if the new 5 cent is inserted, then it should go to the next state, which is 10 cent received. Okay, and so on. So at the end, 15 cent, which means at least 50 cent has been received and accumulated, then the machine should produce open equal to 1 as the output, so that signal can go to the next component, mechanical component, to release the gum. Okay, so this is the optimized state diagram. You can translate it to the symbolic state table as step 3 in the design of finite state machine. Okay, so for symbolic state table, there are 4 types of columns. The first column is the present state, the second column is the inputs, the next column is the next state, and the last column is the output. So it is something like truth table, so you have to first fill out the present state and inputs in the systematic order, where if we have the present state label as 0, 5, 10, 15. So just list them in that proper sequence: 0 cent, 5 cent, 10 cent, 15 cent. Okay, and then for each present state, list down all the possible values of the inputs. So because as I mentioned earlier, so from each state, how many outgoing branch that will come up from the state, it depends on the it depends on the number of combination values of the inputs. So since we have two inputs, so the combination value we have totally is 4, 0, 0, 0, 1, 1, 0, 1, 1. So actually in the complete step, you need to consider 4 outgoing branches for each state. Okay? So 5 cent also you need to consider if 0, 0, what happened to the next state, 0, 1, what happened to the next state, from 5 cent, 1, 0, what happened to the next state, and so on. Okay, so this is how you list down in a proper sequence and order for the present state column and input column. And for the next state and output, for the column of next state and open. Okay? So next state and open are determined by the behavior of the finite state machine. So you just need to refer to the state diagram to fill up the next state. So how do you fill up? So for present state, if currently this machine is at 0 cent, which means no money is received or accumulated, and the coin D equal to N, D equal to 0, N equal to 0, that means there is no coin inserted, then the machine should stay at 0 cent. But if there is one coin, which is a 5 cent received, then the state machine should move to the next state, 5 cent. But from 0 cent, if 10 cent is received, then it should go to 10 cent state. D equal to 1, N equal to 1, as mentioned earlier, is an impossible case, so you can put don't care by assuming this will never happen. And during present state 0 cent, open is still 0. Okay, open will only become 1 when the state is 15 cent. Okay, so similarly, you can derive or fill in the next state value for 5 cent. 5 cent, D and N 0 still waiting, so it will stay as 5 cent as accumulated amount. But if from 5 cent, the one new coin 5 cent received, then accumulated, it will become 10 cent, so the machine should move the next state 10 cent. But from 5 cent, if 10 cent is received, then the machine should move directly to the 15 cent. 1, 1 again is an impossible case, so you can put don't care. So the same thing you can do for the next two states, and this is a complete symbolic state table you get. So for the next state, you just need to translate the symbols to the coding after you decide which encoding method you want to use. So normally we just use a binary encoding, which means we just translate, give the coding of 00, 0, 1, 1, 0, and 1, 1 to each of the states respectively. So 0 cent, we give the code 00 to represent 0 cent. As 5 cent, we give 01 to identify as an identity for the 5 cent, 10 for the 10 cent, and 11 to represent the 15 cent. Because circuit can only understand signals, or digital circuit can only understand binary signals. So you, instead of symbol, you need to make all the symbols binary values to represent them. Okay, so similar, go to the next step. So you just, once you have decided 0 cent represented by 00, then all the 0 cent should be replaced by 00. All the 5 cent replaced by 01, and all the 10 cent symbol replaced by 10, and all the 15 cent symbol replaced by 11. Okay, so after you have the complete encoded state table, then you can move to the last step, which is the implementation. So this example shows the implementation using schematic. So to use the schematic or to derive the schematic for the FSM, first you need to solve the Carnot map for the next state logic and the output. So how do you know how many Carnot map you need? So you refer to the encoded state table just now. You have next state that consists of 2 bits. The next state consists of 2 bits, which is D1 and D0, and then you have a 1 bit for the output, which is open. So totally you have 3 Carnot maps to solve to get the complete schematic for the FSM. Okay, so you fill out the Carnot map based on the encoded state table. Okay, so for D1 column, and then for when present state is 00, okay, present state represented by bit Q1, Q0, present state 00, D0 and 0, then the next state bit D1 is 0 based on the encoded table. So just fill up 00, 1x, 01, 1x as listed down in the encoded table. The same way you do, you fill out all the Carnot map, then you solve it using the method you have learned in digital electronic, which is to circling for SOP solution. You just circle the largest group of ones, including manipulating the don't care. If don't care, since don't care can be 0 or 1, just you decide don't care as 0 or 1 to make the circles as large as possible. Okay, the grouping of the ones as large as possible. Okay, so with this, then you solve the K-map, and then D1 you get Q1 plus Q1 or D or Q0 and N. So you can draw the gates. Q1 here, or with the D, this is the OR gate, and or with the result of Q0 and with N. Okay, Q0 and with N is the AND gate, and the result will be all together with Q1 and D. And then you produce the first bit of the next state, and then connect it to the state register or the flip-flops, and then where the output of flip-flop is the present state. Okay, so open is just Q1 and with Q0, implemented or realized by using one single AND gates, and totally you need 8 gates to realize the finite state machine for the vending machine. Now let's look at the second example. So this is a finite string pattern recognizer that recognizes the string 010. Okay, 0, 1, 0. Okay, recognize 0, 1, 0. So that means whenever 0, 1, 0 is observed or detected, then the output will be 1. Asserted means the output will be 1. Okay, but however, if 1, 0, 0, the stop pattern is detected, then after stop pattern is detected, then the finite string recognizer will not function as a 0, 1, 0 detector anymore. So it will stop detecting. Okay, so after stop pattern 1, 0, 0 is detected, it will stop detecting. So let's look at the samples of simulation or samples of input output. Okay, so just now the first strategy, when you try to understand the vending machine, you draw the diagrams. So it depends on the spec, what kind of technique you want to use to make sure your understanding of the spec is as good as complete as possible. So if it is about the string, then you just do some simple manual simulation to check your understanding. Okay, so if 0, 1, 0 is detected, you see here the output become 1 in this simulation. Another 0, 1, 0 detected, output is 1. But here at this point of time, 1, 0, 0 is detected. Once 1, 0, 0 is detected, then you see the next 0, 1, 0 detection won't give any 1 anymore at the output. Okay, so similar, go to the second sample of the input output that helps you to understand the spec of the finite string pattern recognizer. Okay, step 2, draw the state diagram. So you can start with the initial state S0. Okay, that means no bit is detected. Okay, and then start with since this system has only one bit in one input, one bit input. Okay, so the input at one time is either receiving 0 or 1. So we just need to consider 2 outgoing branch from each state. Okay, so S0 receiving 0. That means this 0 represents the first bit of the 0, 1, 0 string. Okay, so you can move to the S1. That means S1, you can put a remark there. S1 means the first bit has been detected. However, if the first bit is 1, that means this is the first bit of the stop pattern. S4 is the first bit of the stop pattern detected. Okay, and then you can proceed, and then you can draw the partial of the state diagram. The left side represent 0, 1, 0 detected, and then the output will be asserted, output equal to 1. The right side represent the stop pattern detected, 1, 0, 0. Okay, and then after 1, 0, 0 detected, there is a loops, forever loops in the S6. That means after the stop pattern 1, 0, 0 is detected by the FSM, it will stop detecting stop doing the jobs of detecting the 0, 1, 0. That's why it loops here forever until somebody reset the system. So the state diagram is not stopped there. State diagram must be made complete. How do you know the state diagram is complete? As I mentioned many times, each state need to consider all the possible combination values of the inputs. Since this FSM has one input only, so there are two, at most two. You need to consider 2 outgoing branch for each state to make sure it's completed. So 2 means the first branch is when in equal to 0, the second branch when input equal to 1. So for S1, it's not complete yet because so far you have only considered when input equal to 1. What about when input equal to 0? Okay, and then same goes to S4, S2, S5, and so on. So we try to complete it. So now I think this one we start with S3. Yeah? S3. Okay, so S3, the outgoing branch we need to consider is when input equal to 0 and when input equal to 1. Okay, so after 0, 1, 0 is detected, and then it's followed by new bit 0. That means it is a stop pattern detected. Right? Because you see 0 at S3, 0, 1, 0 is detected so far. But if the new bit coming in is 0, just imagine the new bit coming in is 0. That means it complete the pattern of 100, which is the stop pattern. Then it should go to the S6 that represent the detection of the stop pattern. Okay, but if 1 is detected, let's say from S3. So far 0, 1, 0 is detected. If 1 is detected, it's a part of the 0, 1, 0, which will go to the S2, which means the second bit of the 0, 1, 0 is detected. Okay, so similar way you complete, make sure all the states have 1 and 0 outgoing branch. As mentioned, when you draw the state diagrams, please make sure you have the remarks that describe the definition of each state. So it will help you a lot in deciding the transition, the correct transition of the states. So from the state diagram, you derive the symbolic state table. So the method how to do it is the same. You just list down all the present state and input in the according sequence, okay, and then fill up the next state and the output based on the state diagram. And now I would like to further into the implementation step, but for this example, instead of schematic, let's try the implementation in Verilog. Okay, so for implementation in Verilog, you don't need K-map or cannot map. So, but first you need to make sure you're clear with the concept of the 3 blocks that compose the finite state machine. So in this case, the solution shown just now in the state diagram indicate that we are using more finite state machine. So for more finite state machine, the next state logic depends on the input and the present state, and the output logic depends on the present state only, because this is more machine. Okay, and then the middle one is the state register of the flip-flops that holds the present states. Okay. So whatever next state's value coming up from the next state logic will feed to the state register, and after clock trigger, then the next state value will become the present state. So based on this diagram, for Verilog implementation, you just need to code 3 always block. Okay, for next state register, and output logic. Code them based on the behavior of the state diagram or based on the state table. Okay, so based on the state table, let's first code. You have 3 always block. You can code any block, any sequence of the always block, because always blocks are concurrent to each other. That means the execution of the lines inside here as a behavior of the hardware happen in the concurrent way or simultaneous way. Okay, so next state logic. So always block in the sensitivity list, you put present state and input, because always block for the next state. As you can see, the next state logic here depend on the input and the present state. Okay? And then for each present state, okay. So describe the transition. What condition will transit the S0 to S1? What condition will transit S0 to S4? All these you code based on the encoded state table. Okay. And then for output, same also go to output logic based on the encoded state table beside the output value. So output value will be 0, except that when present state is S3, because it already detected 0, 1, 0, so output will become 1. Okay. And for the flip-flop block, it is actually for the state register. You just need to code it like a register. So if we set the present state, the output of the register will be S0, okay, going back to the initial state. And if not reset, then the present state will just receive the next state value, be S equal to NS. Yeah, so this is what I explained just now. You want to code based on, just refer to the encoded table. Okay, next I would like to further explain how to verify the Verilog coding you have done using the Testbench. Okay, so previously you have learned how to use the waveform method to, like shown here, to verify whether the design worked correctly. For example, here the waveform show 0, 1, 0 detected already, then the output should be 1. And then 1, 0, 0. This one stop pattern detected. Before stop pattern, another 0, 1, 0 detected here, so the output become 1 again. But 1, 0, 0, after 1, 0, 0 detected, so the output should be 0 until the system is reset. It won't become 1, even the third 0, 1, 0 is detected here, it won't become 1 because the stop pattern has been detected, and that means indicating it will stop functioning for the detection. Okay, so how do you, instead of using waveform, how do you describe the signals you want to pump into the circuit in Verilog? And then how do you monitor the output in Verilog? Okay, first you can use module. Name the testbench. No need to put anything in the bracket because testbench doesn't have input output. Testbench is not a circuit. Okay, so you just need to use variables to name the variable you want to connect the testbench stimulus and output. So in this case, you write testbench to produce the signal, clock, reset, and in. Okay, I repeat again, you write testbench to produce the signal, clock, reset, and in. You're going to write them in using the sequential block. You have learned before, always is one of them. Initial is another sequential block. So whenever you use initial or always, whatever signals produced must be declared as a type rec. That's why you put rec, clock, reset, in. Okay, I repeat again, why rec, type rec? Why type rec for clock, reset, in? Because you're going to write using a sequential block, which is initial here, to produce signal, clock, reset, in. Okay. And then the signal that come out from the circuit, which is out here, will not go out anywhere. It will be observed inside the same testbench. Okay, put that I here observing the same testbench. So the signal is not going out, so you don't need to declare it as an output. There's no output for testbench. You just make it a type wire. Okay, so because you are going to connect this output, this wire output to a command to observe it. Okay, so now let's see how do you use initial block to describe or generate the signals. Okay, so initially you put everything 0 because it as shown in the waveform. Initially the clock is 0, reset 0, input also 0, put everything 0. Okay, and then after 7 nanosecond later, let's assume the unit of time is nanosecond, and the hash 7 here means how many unit of time later. Okay, so hash 7, if the unit is nanosecond, that means after 7 nanosecond later, the reset become 1. Yeah, reset become 1. And then if there's no change after that until the end of the simulation, then you don't need to mention again reset here until the end of the simulation. Okay, and then for in, there's a change from 0 to 1 somewhere in this time, which is 40 second later, 40 nanosecond later. Okay, so 40 nanosecond later in become 1. So as described, 40 nanosecond later in become 1. So the 40 nanosecond later is not counted from the beginning of the time. It's counted from the last statement you mentioned about the time. Okay, so that means 40 nanosecond later means 47 nanosecond later from the beginning of the time. Okay, if you count from beginning of time, it's actually 7 plus 40, which is 40 nanosecond. 47 nanosecond later, the in will change to 1. Okay, and then another 20 nanosecond later, in become 0. Another 20 nanosecond later become 1. 20 nanosecond later become 0. And then another 40, now this one longer, 40 nanosecond later it become 1 again, and 20 nanosecond later it becomes 0. So this is how you describe the waveform input waveform that you want to supply to the circuit. And then after the in becomes 0, 20 nanosecond later you finish the simulation. Then you don't forget to put the finish $finish here to tell the compiler the simulation finish at this point of time. So this is about how you describe reset and in. For clock, we separately describe it in another sequential block, which is always block, because the signals are regularly changed, okay? Like every 10 nanosecond toggle, right? So you can separately, it's more convenient to separately describe it using another block, always block, where #10 clock equal to toggle clock. That means every 10 nanosecond we toggle the clock signal. Then we get this kind of clock pulses for the simulation. Okay, so alternatively, you can use a separate, instead of always block, you can use a separate initial block to initialize the clock, the CLK, sorry, the clock equal to 0. Then you use the construct forever to toggle the clock for every 10 nanoseconds. So this should be, sorry, some typo here, clock CLK and every 10 nanoseconds. Okay, so this is the initial construct you can use to produce the clock signals here. Okay, so I repeat again, clock, the first method you want to describe the clock, you can put the initial value in the initial block, and then you can repeat the toggling of the clock pulses using the separate always block. Or alternatively, you can use one single initial block, and then initial the clock equal to 0, and then use forever under initial block to show the toggling of the clock for every 10 nanoseconds. Okay, so lastly is about the output you want to observe. So for output you want to observe, you put it in another initial block. Use monitor. Monitor is like the print out or the print function in your programming. So what you want to print, you put in a string. Okay, so I want to print out time, the word time, followed by some integer. Okay, and then continue with the string column reset equal to some binary value. Okay, b binary value, clock equal to, this is the string I want to print out, followed by some binary value. So what decimal value, binary value you want to print out here, you can mention it after the string. So after the end of the string, you close it with a double quotes, comma, and then you put all the variables you want to print out, which will be printed out in the percent, decimal, percent binary here. So the first one I put is the $ time. That means when you run this code, what will print out here is the simulation time. So at this simulation time, the reset value, okay, how the compiler know you want to print out the reset value, because you put the name of the signal reset here as the second parameter to print out. Okay, the third parameter to print out in the binary format is clock, and the next value to print out is input signal value, and followed by the output signal value. So when you run this, there will be multiple lines printed out. So a good thing about using monitor command here is it will only print out every time there's a change. There's a change happen to one of the signal here. If there's no change, then you print out once only. Then you first print out once. If there's no change afterward, you will not repeat the printing. So it's good for the debugging because you don't need to see the same lines repeatedly printed out. Yeah. And lastly, don't forget to instantiate the circuit you want to verify in the test bench. Okay. So test bench consists of the waveforms to supply to the circuit, how you monitor the output, and instantiation of the circuit you want to verify and connect the signals to them. Clock, reset, in are the signals in this test bench that we have described the waveform. So you make sure you connect it so that the waveform will reach the circuit, and the output will be produced by the circuit, and then it is of type wire. Then it will connect to this monitor command for you to observe. How to observe? The simulation will print out the lines every time at least one of the signal here change value. The third example is the traffic light controller. So let's try understand, read the specification of the traffic light carefully. So it's an intersection road where there's a farm road which normally have less cars, and there's a highway which normally have more cars. Okay. There's a detectors embedded buried on the road of the farm road to detect whether the car is there or not. So normally the highway will get the priority, okay, of the traffic light green. Okay. So in this traffic light design, only when a car is detected on the farm road, okay, say the yellow car detected on the farm road, and the highway light will finish the green interval it has, for example 3 seconds. It will finish the 3 seconds it has, then it will give way to the farm road car because the car is detected. Okay, but if the car is not detected, then highway will get a priority to have continuous green in for a longer interval. Okay, so from the spec, then you should be able to identify that there are some inputs going to this traffic light controller, which are car sensor on the farm road, and the short interval signal that should normally come from a timer outside of FSM that count the short interval has reached or expired, and another input is to tell the FSM the long interval has expired, okay, which also come from the timer. So why we have these two kind of signal? Because when traffic light become yellow, it will stay yellow for a short interval. So this is actually counted by a timer. So the FSM will wait the timer to tell it the yellow interval reached or expired or not, so that it can do the next instruction, produce the next instruction to change the light. Okay, long interval is for the green and the green light interval. Okay, so the output of the FSM is the highway green light, highway yellow light, highway red light, and farm road green light, farm road yellow light, and farm road red light. And there's one additional signal ST, which means start the timer, that will connect to the timer outside the FSM. The FSM need to instruct the timer when to start counting the yellow interval, when to start counting the green interval. So After you are clear with the specification for traffic light controller, now we come to the second step on deriving the state diagram. So we have three inputs for the traffic light FSM, which are long interval, short interval, and car sensor. So make sure all the combination values for the three inputs are considered for each state to decide all the possible outgoing branches or transitions from the state. For instance, let's say from S0, where S0 means the highway road traffic light is green. So how many outgoing transition from S0? So you need to consider in complete way, you need to consider all the possible values for TL, the long interval, car sensor, and short interval. However, short interval is considered as don't care when highway is green, right? Because as explained in the previous slide, short interval is for the yellow light. So you just need to consider all the possible values, combination values for the two inputs remain here, which are long interval and car sensor. So for a careful step to derive the transitions out from S0, you can build a simple truth table and list down all the possible value, and then think in the actual situation for the traffic light where the transition should go. So first one, 00 mean when the long interval is not yet expired, the green light interval is not yet expired, and there is no car on the farm road. So what happened is the state should stay S0, which means it should be green continuously for highway. Second situation is when 01, when the green light interval is still not yet expired, but there's a car waiting on the farm road. Because of the interval not yet expired as specified in the specification, so the green light should stay green. So S0 stay as S0. Okay, the third situation is when the interval reach is the green light interval has expired, but there's no car waiting on the farm road, so we don't need to change the light instead, because the highway get the higher priority, so highway will stay green. Only when the situation described here where the green light interval has reached or expired and the car is waiting on the farm road, then only the state should transit from highway green to highway yellow, so that can give way to farm road car to get a green light. Okay, so how you label here, you can use some Boolean expression that representing the values. So just now we said only TL equal to 1 and C equal to 1, transitions will happen. Then you can write TL and C for the transition from S0 to S1. Okay, so this is a mini machine. So after slash we put the input. After slash we put the output. Okay, so the remaining condition can be represented by TL bar or C bar, where it actually refers to the three situations here. Like either TL is 0 or C is 0. If one of these is 0, then the transition, the next state should be staying at S0. For output, as you learned earlier, the output is the ST signal that is to enable or to tell the timer to start counting the interval. So when the S0 stay as S0, the ST is not labeled here after the slash, so that means ST equal to 0, which also means the timer no need to restarted for counting the interval. Okay, so ST is a signal or a pulse that tells the timer to start counting the interval. So while S0 stay there, where the green light the green light interval is still counting, there is no need to restart the timer. That's why ST is equal to 0 that time. Only when highway green change to highway yellow, then we need to give a pulse of signal ST equal to 1, so that the timer will restart counting for the short interval, which is for for yellow light interval. So once it enters the yellow light state, then it will stay as a yellow light as long as the short interval, the TS, don't confuse between ST and TS. ST is to start the timer. TS showing the short interval, the yellow light interval is not yet expired, so it will stay at S1 until the yellow light expired. Then it will create a pulse again for ST to restart the timer, so that timer now when entering S2 will start counting for the green interval for the farm road. Okay. So farm road, well, the same thing you need to do for the outgoing branches or transition for farm road. You can draw a simple truth table and check when should the farm road stay green, when should the farm road change to S3, which means farm road yellow, to give way to the highway car to get green light. Okay, so this is how the state diagram look like. So we due to the space limit, we don't show the remaining outputs. Remember, there are other outputs apart from ST. There are the LED light, the highway green light, highway yellow light, highway red light, farm road green light, farm road yellow light, and farm road red light. So all these 6 are actually also the outputs of the FSM, which should be labeled here. But we know the light follow the states. Okay, so when S0, when highway is green, then we know S0 also mean highway green light is on, and farm road, red light is on. Okay. So S1 is highway, yellow light is on, and farm road still stay red. S2 means highway turn to red and farm road light is green. S3 means farm road light is yellow and highway light stay red. Okay, so after the step 2, step 3 is to derive the state table, where the first column is present state, and followed by the for each state we list down all the possible values for the inputs. Then we'll fill up the next state based on the state diagram, and output based on the state diagram also. So because we know some of the inputs are not required to be considered in some particular state, we can use don't care to make the table more compact and easily for it to read. I mentioned just now, S0 will stay as S0 when either TL equal to 0 or C equal to 0. You can, so the first row you can put 0 and other don't care. So the next state is S0 and the start timer signal is 0, and the light as mentioned is highway green and farm road red. So the second situation is when C is 0, so and other don't care. So you fill up the next state and output. The transition only happens when TL equal to 1 at the same time C equal to 1 as shown here. And then we don't care about the S because short interval is for yellow light. Then you fill out the next state is S1 because it's S1, and ST, the start timer signal is on, and the light actually depend on the state only. So you can see here only ST, the output, the only output ST depends on the state as well as the present state to determine the value. So ST make the FSM milli, but the remaining outputs actually it depend on the present states. As long as there is one milli output, then the whole FSM is considered milli FSM. So based on the table, then you can choose the encoding, which is binary coding. So the encoding need to be described in the Verilog. Say the implementation method is Verilog. So we choose binary encoding. So S0 will be encoded as 00, S1 as 01, S2 as 10, and S3 as 11. So once you describe the encoding, then you can use the symbols in the following coding. So remember, for FSM, you just need to make sure you have 3 always blocks. The first always blocks, one of the always blocks represent the next state logic, and this one is the output logic. One of the always block is the output logic, another one is for the next state logic, and the last one, the simplest one, is for the state register or the flip-flops that hold the present states. Now let's look at the last example, which is door combination lock. So this is a door system that needs the user to enter 3 digits in a sequence before the door can open. The door can only open if the 3-digit password is correctly entered. Otherwise, it will enter the error state and stay in the error state until the user reset the system. So the input is the sequence of input digits and reset and clock as usual, and the output is the open to indicate whether the door is unlocked or not. And memory means the state registers or flip-flops that need to hold the present states. Okay, but when you have the specification here, the input output for the FSM it may not be a complete one, so you need to do some analysis or do some drawing of the block diagram, and even drawing the ASM chart, and also consider the data path components this system needs, so that you can come up with a complete input-output list for your FSM. First, let's look at the ASM chart for the whole system. Okay, so remember, if you are asked to design the FSM only, it's good that you start to understand the whole system using the ASM chart, because it will help you to identify the data path components, and through the understanding of the data path components, you can derive more accurately and more complete way the inputs outputs you need for the FSM. Okay, so ASM chart for the door combination, a simple system. The first state is start with the state box, and in the state box normally we will label the output or register that we want to update. Okay, so the state box, the first state box is S1 open equal to 0, that means the door is still locked, and then it is checking whether a new digit is entered. So the new here is something like the enter button. If a new digit is entered, user will press the enter button. So if it is not pressed, then it will wait here, waiting for the user to tell when a new digit is entered. Once the system detects new, then it will go and check the value or the digit entered by the user is equal to the stored digit or not. C1 is the stored digit for the first digit, password digit. Okay. then if correct, then only you move to S2 to do the same process to check or compare the second digit of the password. Okay, and then if correct, only you go to S3 to check the third digit of password, and if the third digit correct, then it will only it will enter the open state to open the door. But for while checking every digit, once the system detect the one of the digit is wrong, then it will move and enter into error state and then lock the door and have a self loop there, which means the door will be locked forever until somebody come and reset the system. So from this ASM chart, let's identify the process that related to data. So the process related to data is comparator here, because it compares two data, two digits, the digit entered by the user and the digit stored earlier as the C1, the first correct password. So we know that our data path components need a comparator that take down the stored password C1 to be compared with the user entered digit. And S2 involves the data comparison for C2 and S3 for C3. So actually there are three comparisons taking place here, but if you want to save the comparator in your hardware, then you can just use one comparator and use a multiplexer to choose which digit to compare, because as we know, all the three digits will be compared at different states, which means different time. So in fact, we can share the hardware. Okay. So because of these data path components, you will see that you need the signal called mark select to select which digit to be compared, and the comparator will produce equal. So this mark select is not the input of the overall system. Instead, it is expected to get the signal mark select from the FSM, because FSM plays the role as a controller to control and instruct how the data path components works. And comparator output, which is the equal, will be fed or connect to the FSM to tell the status of the data, so that the FSM can make decision what to do, how to instruct the data path components next. Okay, so after knowing that the signals that we need to include in our FSM, so during the previous slide that showed the specification, we still cannot see that our FSM actually need mark select as the output and equal as the input. But after you do these steps of analysis using the ASM chart and deriving the data path components, now you see that your FSM also need to have output call mark select and input call equal. Okay, repeat again: output call mark select, input call equal. Okay, now replace those signals. Make sure you place these two signals in your ASM chart. Okay, so where do you need to put the mark select in the FSM chart? Since it will be your FSM output, so you need to put it in this ASM chart. You need to put it in the state box. Okay, so S1, the mark select will be equal to 1. Will be updated as 1, because during S1 we want the multiplexer to select C1 to go to the comparator for the comparison with the digit entered by user. Okay, S2 we need mark select to be updated as 2. S3 we need mark select to be updated as 3. Okay, so we have done with the mark select. What about equal? Equal will go into your FSM. Okay, to tell your FSM the status of the comparison, so that it can make decision whether to move to the next state S2 or to move to the error state ERR. So we have replaced the since equal coming from the comparator, then we are supposed to be able to replace the comparison condition in the decision box here. So we replace that equality checking with the equal sign, equal signal. So this means when equal is true in state 1, when equal is true, that already means the user entered digit and the C1, the expected correct code number 1, are equal. Then it will move to the next state. Okay? So the equal signal in S2 means differently than the equal signal in S1. The equal signal in S2 means the value entered by the user is equal to C2. Okay? Because mark select at this state, select number 2 to be compared. Okay? Same explanation, go to S3. So from here, the SM chart, you can derive the state diagram. Okay, so S1 is the first state here, and then the output, it is a more machine. The output here, you just need to take directly what you have labeled in the state box as output. Okay, state box, put it in the output. And for the transition, so look at S1 box here. There are three types of transition. One is if new is false, then it will go back to S1. So we can label accordingly. If new is false, new bar, then S1 will go back to S1. Okay. The second transition is if new is true, followed by equal is true, then it will go to S2. And label it equal is true and new is true, then go to S2. And the third transition is if equal is false, then it will go to error state. New is true, but equal is false, it will go to error state. So you see here from S1, new is true, but equal is false, then it will go to error state. So other states also you can derive directly from ASM, as I explained for S1. So you get the state diagram directly from ASM. So now you can see the steps are more structured with the help of ASM and the derived data path components. Okay, this slide shows the overall structure of the door combination lock, where the left side here is the data path, but the FSM just is needed for the right lock, which is designing the controller. So I repeat again why identifying the data path components are very helpful in the FSM or controller design, because as you can see, when after we identify we need a multiplexer to choose the 3 digits to be compared, we realize that we must select signals to be produced by the FSM as the one of the output, and with the comparator output which is equal, which reflect the status of the comparison. This is with the by realizing the existence of this signal in the system, we will realize that we need an equal signal as the input to the FSM, so that the controller know the comparison result and it can make a decision on the transition of the states. Okay, so this slide is just repeating after you understand thoroughly the door combination lock system through the ASM and the data path components. It will help a lot for you to derive the state diagram. So with the state diagram, you can come up with the symbolic state table, where the right column consists of present states and the inputs. So for each present state, you can label this one S1, S2, S3, open, and error. For each present state, list down all the possible combination values for the inputs. So the first one 0x, because when as long as the enter button or the new digit is not entered, we don't care what is the equal result. Okay, then the present state S1 will stay as S1 for the next state, and then when if the new signal is detected or enter is pressed, but the equality is not there, that means the first digit and the first digit entered by the user and the expected first digit is not equal, then from S1 the state will move to error state. Okay, and as long as the present state is S1, the mark select will be 1 to instruct the data path multiplexer to choose C1 for the comparison, and the open equal to 0. You can put open bar to indicate open equal to 0. That means the door is still locked. Okay. So using similar way, you can fill up the state table. So this one S1, you can just put S1 once, or you can just repeat S1 like this, S1, S2, S3. For present state open, as I explained just now in the specification, once the door is open, it will stay at the same state until the user reset the system. So that means we don't care what are the input values when the present state is open. Okay? So the door is unlocked and until somebody reset the system. Say similar goes to the error. Once one of the digits is detected as wrong, then the system will move to the error state and stay there until the system is reset. Of course, the open is equal to 0 because it's an error state and the door shouldn't be unlocked. That is the symbolic state table, but for encoded state table, you first need to decide the encoding style. So you can use the usual way, which is binary, where you just put 000 for the first state, 001 for the second state, and so on. Or you can use other pattern like one hot. One hot is when you have the coding where only one unit or only one bit consists of bit value 1. Okay, so you see here the 1 at the last bit, 1 at the second last bit. So this one we call one hot pattern. So you can use one hot pattern to encode the state. Okay, so the first state is 00001, the second state is 00010. Or you can even use the one hot pattern plus the 0 to encode the states. Okay. Also in the symbolic table, sometimes we don't put the marks value in binary. Make sure in the encoded table you have to put it in a binary. So in mark select, we put 1, 2, 3 in the symbolic table. So we can decide to put it use a binary way where 1 is 0, 1, 2 is replaced by 1, 0, and 3 is replaced by 1, 1. Okay, so open is either 0 or 1. Okay, which 1 mean open, 0 mean close. So replace all the symbols with the binary codings and you get an encoded state table as shown here. So with this, you can proceed to the implementation either using Verilog coding or schematic method. That's all for all the 4 examples of finite state machine. I hope this lecture helped you improve your understanding on FSM design. Thank you.